Okay, hi. So we're up to module 12 of ENSA, which is network troubleshooting. So in this module, we're going to cover network documentation. So of course, very useful for knowing how the network should be set up. Troubleshooting process, so the process going from start to finish and how you would troubleshoot things. Troubleshooting tools, symptoms and causes of network problems, and troubleshooting IP connectivity. All right, so documentation. And so accurate and complete network documentation is required to effectively monitor and troubleshoot networks. Common network documentation includes the following: physical and logical network topology diagrams, network device documentation that records all pertinent device information, network performance baseline documentation, and all documentation should be kept in a single location, and backed up documentation should be maintained and kept in a separate location. So when it comes to topology diagrams, there's two types. There are physical and logical topology diagrams. So of course, physical shows you where in the building cables run and where devices are located and the like, while the logical is more about the addressing scheme, so layer 3, and how what devices can interact directly with one another and or how networks connect together. Now, device documentation. So basically here you can see that we've got documentation for routers, switches and end systems. And so it should contain accurate, up-to-date records for the network hardware and software. Documentation should include all pertinent information about the network devices. And so of course on a router, a lot of that information would be about all the different interfaces and models and serial numbers and other things like that. Of course, certainly could be useful. Versions of operating systems as well. So switch is much the same, only with that, you'd probably talk more about what VLANs, what ports are used for inter-switch links and things like that. And then the end system, of course, is you'd have device names, what operating system, what they do, MAC addresses, IP addresses, and things like that. Now, a baseline is another piece of documentation you can create. So it's used to establish normal network performance to determine the personality of a network under normal conditions. Establishing a network performance baseline requires collecting performance data from the ports and devices that are essential to network operation. And so, it provides insight into whether the current network design can meet business requirements, can reveal areas of congestion or areas in the network that are underutilized. So what data do we collect? So when conducting the initial baseline, start by searching a few variables that represent the defined policies. If too many data points are selected, the amount of data can be overwhelming, make analysis of collected data difficult. You start out simply and fine-tune along the way. Some good starting variables are interface utilization and CPU utilization and the like. And so identify devices and ports of interest. So a logical network topology can be useful in identifying key devices and ports to monitor. As shown in the sample topology, the devices and ports of interest include PC1, the admin terminal, 2 servers, router interfaces, and key ports on switches. When capturing data for analysis, the period specified should be at a minimum 7 days long, last no more than 6 weeks unless specific long-term trends need to be measured. Generally, a 2 to 4 week baseline is adequate. Conduct an annual analysis of the entire network or baseline different sections of the network on a rotating basis. Analysis must be conducted regularly to understand how the network is affected by growth and other changes. All right, so what can we use to measure items? And so show version will give you uptime, and of course version information for the hardware and the software. Show IP interface gives you a lot of statistics about interfaces. Show IP interface gives you configuration information. Show IP route, of course, shows you the routing table. CDP neighbors, of course, gives you detailed information about connections between Cisco devices. ARP tables, neighbor tables, and so on and so forth. So lots of good information there. All right, so the troubleshooting process. Troubleshooting can be time consuming because networks differ and problems differ. And of course, troubleshooting experience varies. Using a structured troubleshooting method will shorten overall troubleshooting time. There are several troubleshooting processes that can be used to solve a problem. The figure displays the logic of flowchart of a simplified three-stage troubleshooting process. So of course, the start of it all is when you or one of your customers notices that there's a problem, and so then you start gathering symptoms. And so from those symptoms, you start to isolate what problem it could be, and then from there you implement a corrective action. Now, if you're lucky, first time you do that, it will be fixed, and so you can document the solution and away you roll. But of course, your first theory may not be the correct theory. If it did not fix the problem or it created another problem, undo that corrective action and start again. So then it's an iterative process. All right, well, theory one didn't work, so we go back to stage one. All right, are there any more symptoms? All right, so what theory two, is that what it is? And so basically you cycle through that until you fix your problem, and then you then you document the solution. 7-step troubleshooting process. And so again, we've got a flow chart. And so we define the problem. So verify that there is a problem and then properly define what the problem is. Then you gather information. So targets are identified, accessed and information gathered. You analyze the information that you've gathered. And so from that, you can identify possible causes using network documentation, baselines, knowledge bases and peers. You can eliminate possible causes, progressively eliminate possible causes to eventually identify the most probable cause. Propose a hypothesis. When the most probable cause has been identified, a solution must be formulated. You then test the hypothesis, and so from there you should be assessing the urgency, create a rollback plan, implement the solution and verify the outcome. And so solving the problem, when solved, inform all involved and document the cause and solution to help solve the future problems. All right, so when you're questioning end users, here are some sort of guidelines, basically. You should ask pertinent questions. And so things like, what does not work? What exactly is the problem? What are you trying to accomplish? And then you try and determine the scope of the problem. Who does this issue affect? Is it just you or others? What device is this happening on? Determine when the problem occurred or occurs. When exactly does it happen? When was it first noticed, and were there any error messages displayed? Determine if the problem is constant or intermittent. So can you reproduce the problem? Can you send me a screenshot or video of the problem? Determine if anything has changed. What has changed since the last time it did work? So maybe a device has been changed or setting or whatever it might be. And then use questions to eliminate or discover possible problems. So what works, what does not work? Okay, so some common commands used to gather information. Of course, you can ping. So that's basically telling you what works and what doesn't. Trace route, of course, will give you a little more extra information about paths and also how far you can get. Telnet, of course, can be used as your solution to connect to remote devices. Of course, SSH is better. SSH does much the same thing, but more securely. And so, of course, you can then use your show commands for information to gather. So show IP route on a router by all means. All right, so troubleshooting with layered models. The OSI and TCP/IP models can be applied to isolate network problems when troubleshooting. The figure shows some common devices and OSI layers that must be examined during troubleshooting process for that device. And so, of course, end systems are application layer devices. Routers and multi-layer switches, of course, are layer 3, and of course they can do layer 4 stuff as well. Standard switch is layer 2, and a hub is layer 1. You'll see many of them these days. So structured troubleshooting methods, and so basically there's several approaches you can come up with, and so the first 3 are basically all around the OSI model, bottom up. So basically you start at the physical layer and work your way up. Is the physical layer working? Great. Data link layer, network layer, up the stack. Of course, top down is basically start with the top layer. If that's working, you can pretty much finish, I suppose. Maybe there isn't a problem. But if it isn't working, then you can go down to transport layer, network layer, and so on. Follow the path used to discover the actual traffic path from source to destination to reduce the scope of troubleshooting. Substitution, you physically swap a suspected problematic device with a known working one. You can comparison, so attempts to resolve the problem by comparing a non-operational element with a working one. And an educated guess, success of this method varies on your troubleshooting experience and ability. So experience comes in a lot with educated guesses. The more experience you got, the better educated you guess. All right, so guidelines for selecting a troubleshooting method. To quickly resolve network problems, take the time to select the most effective network troubleshooting method. The figure illustrates which method could be used when a certain type of problem is discovered. Troubleshooting is a skill that is developed by doing it. Every network problem you identify and solve gets added to your skill set. And so basically they're just saying that if it's a software-oriented problem, you might start at the top down. If it's hardware oriented, you might go for them bottom up. And then, of course, things like, how much experience have you had with similar problems? All right, so the process. So common software troubleshooting tools include the following. So network management system tools. So device level monitoring, configuration and fault management tools. We did do a chapter on that not long ago. Tools can be used to investigate and correct network problems. Knowledge bases, and so of course online device vendor knowledge bases have become indispensable sources of information. When vendor-based knowledge bases are combined with internet search engines, a network administrator has access to a vast pool of experience-based information. And then baselining, many tools for automating the network documentation and baselining process are available. And so the tools help with common documentation tasks such as network diagrams, update network software and hardware documentation, and cost effectively measure baseline network bandwidth use. Okay, protocol analyzers. So a protocol analyzer can capture and display the physical layer to application layer information contained in a packet. Protocol analyzers such as Wireshark can help troubleshoot network performance problems. So, of course, we have looked at Wireshark in the past. Hardware troubleshooting tools. And so, of course, digital multimeters will allow you to measure voltages, currents, and resistance. Cable testers are basically just specialised multimeters, really. They have just extra information. Of course, you can test out your communication cables. Analyzers, and so they just sort of go a little further. Portable network analyzers can sort of be a cross between your cable analyzers and your protocol analyzers, actually. Of course, you're going to be paying for them. And then Cisco Prime NAM, which is a browser-based interface that displays device performance analysis in a switched and routed environment. Okay, so Syslog server is a troubleshooting tool. And so this was last week, wasn't it? And so Syslog is used by Syslog clients to send text-based log messages to a Syslog server. And so log messages can be sent to the console, video lines, memory, or Syslog server. Of course, we're talking about the latter. iOS log messages fall into one of 8 levels, from 7 debugging up to 0 emergencies. And so the lower the level number, the higher the security level. By default, the console displays level 6 debugging messages. In the command output, level 0 to 5 notifications are sent to the Syslog server, and so on. So they're doing logging trap notifications, which of course is level 5. And so, and so of course that's the server that's doing the Syslog server, and logging on, of course, needs to be turned on for it to work. Okay, symptoms and causes of network problems. So performance lower than baseline requires previous baselines to be compared with. The most common reasons include overload or underpowered servers, unsuitable switch or router configurations, traffic congestion or low capacity link, and chronic frame loss. Loss of connectivity could be due to a failed or disconnected cable, and so you can verify that with a simple ping. Intermittent connectivity loss can indicate a loose or oxidized connection. Network bottlenecks or congestion. If a route fails, routing protocols called redirect traffic to a suboptimal route. This can result in congestion or bottlenecks in those parts of the network. High CPU utilization rates indicate that the device is operating or exceeding its design limits. If not addressed quickly, it could cause it to shut down or fail. And then console error messages reported on the device console could indicate a physical layer problem. Console messages should be logged to a central Syslog server. See the previous slides. All right, so physical layer troubleshooting. So of course you can have power-related problems. And so hardware faults, so faulty or corrupt NIC driver files, bad cabling, grounding problems can cause network transmission errors such as late collisions, short frames, and jabber. Cabling faults, look for damaged cables, improper cable or poorly crimped connectors. Suspect cables should be tested or exchanged with known functioning cables. Attenuation can be caused if a cable length exceeds the design limit for the media, or when there is a poor connection resulting from a loose cable or dirty or oxidized contacts. Noise, we're talking about electromagnetic interference or radio frequency interference. And so, of course, that can upset data getting through as well. Interface configuration errors, so you can have incorrect clock rates and sources and the like. Exceeding design limits. Component could operate suboptimally if it is being utilized beyond its specs. And CPU overload, and so input queue drops, slow performance, SNMP timeouts, no remote access, no DHCP services. Telnet and pings are slow or fail to respond. Okay, so data link layer, no functionality or connectivity at the network layer or above. Network is operating below baseline performance levels, excessive broadcasts, and then console messages. And so, yeah, there's a whole pile of problems that can be for that. Data link layer again, you can have encapsulation errors. You can have address mapping errors, and so of course that's your ARP or neighbor discovery. Framing errors, and so that can be NICs, cables, duplex mismatches and the like. And then STP failures or loops. So of course spanning tree, if that fails or isn't going, you can have loops, and that's 4. And so again, still with network layer, we've got network failures. Occurs when a network is nearly or completely non-functional, affecting all users and applications of the network. They're usually noticed quickly by users and network administrators and are obviously critical to the productivity of a company. With suboptimal performance, these involve a subset of users, applications and destinations, or a type of traffic. And so optimization issues can be difficult to detect and even harder to isolate and diagnose. This is because they usually involve multiple layers or even a single host computer. You can determine that the problem is a network layer problem can take time. All right, so general network issues. Often a change in the topology may unknowingly have effects on other areas of the network. Determine whether anything in the network has recently changed and if there is anyone currently working on the network infrastructure. Connectivity issues. So you might have power problems, environmental problems, layer 1 problems, and so on. Routing table, check the routing table for anything unexpected, such as missing routes or unexpected routes. Neighbour issues. Check to see that there are any problems with the neighbours, routers forming neighbour relationships. And topology database, of course, is if it's got missing entries and the like. Transport layer, so selection of traffic flow. And so, of course, you can have ACLs that can do that poorly. You can order access control entries can be wrong, so you've got a logical error basically. Some people forget the implied deny any statements, addresses and wildcard masks, and so of course, yeah, easy for human mistakes there. Selection of transport layer protocol. So again, maybe you chose TCP instead of UDP or whatever it might be. Source and destination ports could be incorrect. Established keyword can be applied at the wrong line or something like that. Or if you've got uncommon protocols, you know, so they could be misconfigured as well. So transport layer, again, we've got boot P and DHCP. So in other words, addressing for your host is not working well. So you might need to configure an IP helper address so that the requests actually get to the server. It might be on a different subnet. DNS can be a large problem. Yeah, if you can do it with an IP address but you can't do it with a name, that's a bit of a giveaway for that. SNMP, and so basically, yeah, you might have connectivity issues between the management station and the agents that it's trying to connect to. Tunneling encryption protocols, they do complicate things, and so that can also be broken by NAT. Okay, so of course we've got SSH and Telnet as an application layer protocol, so it's basically a terminal session remotely. HTTP, of course, is how you get web browsers, web pages, and so it's HTML and all the other attached files. FTP is for file transfers. TFTP is for typically smaller file transfers. SMTP, of course, is delivering email. POP, of course, is how you collect email. SNMP is simple network management protocol. So we were talking about that slide or two ago. DNS, of course, is relationships between names and IP addresses. And NFS is sort of like the old Unix version of Samba. It's a network file system that can remotely connect to things. All right, so how do we troubleshoot IP connectivity? So again, we've got the bottom-up approach. When there is no end-to-end connectivity, check your physical layer first, and then from there, you just go up the layers. So duplex, data link and network layer addressing, default gateway, and a correct path. And then from there, transport layer, access control lists, and DNS. All right, usually what initiates a troubleshooting effort is the discovery that there is a problem with end-to-end connectivity. And so two of the most common utilities used are, of course, ping and traceroute. Show interfaces gives you a lot of information, as you can see. And so it's so very good for performance troubleshooting. And so it gives you all kinds of rates, you know, output queue. 0 out of 40, that's not a full queue. The input queue, 0 out of 75, and there's had no drops or flushes. So that's all looking good. And so no input errors, no output errors. All those kinds of things are all good information for you to look at. Duplex mismatches. Of course, auto negotiation normally works, but nothing's 100%, I suppose. And so you might actually need to set the duplex or maybe put it back to default or something like that. Addressing, so of course ARP -A on a host will give you that information of the ARP table. That can be useful information, certainly. VLAN assignments, and so of course you're going to be looking at switches there. and you can do the show MAC address table, which is the equivalent of the routing table, I suppose, but for layer 2. And so from there, of course, you might need to assign a port to a correct VLAN or something like that. Default gateway, of course, each host needs to have a gateway set that's on the same subnet as itself, because they can only talk to other hosts on the same subnet, normal host. So, of course, you need to make sure that that's correct, and of course, checking that they have connectivity to the gateway, of course, as well is another good information. So IPv6. Normally, it will be a link local address. It's normally learnt directly from the router itself, so it's normally good information. But yeah, someone might have blown the addressing on another router as well, or something like that. When troubleshooting is often necessary to verify the path to the destination network. So the figure describes the process for both IPv4 and IPv6 routing tables. The process of forwarding IPv4 and IPv6 packets is based on the longest bit match or longest prefix match. The routing table process will attempt to forward the packet using an entry in the routing table with the greatest number of leftmost matching bits, and so of course that's the subnet mask and or prefix that defines that. Number of matching bits is indicated by the prefix length of the route. So verifying the transport layer. So again, if you can get the application layer to work, I suppose the transport layer is working. ACL, so of course you can do show IP interface, and that will tell you what ACLs are running. And so of course you can do and so, of course, yeah, it's got to be applied to the right interface in the right direction for it to work properly. And of course, yeah, you can do show access lists to actually see what the access list does. DNS, and so, of course, you can do DNS in several ways. If you just ping the host name, of course, that will check DNS as well as connectivity, but of course, you know, you've got NS lookup and a few other things like that that you can use. And so, yeah, that's certainly is an option. All right, so we've hit the end of the chapter. So what have we spoken about in this chapter? We've got common network documentation includes physical and logical layer topologies, network device documentation, as well as baseline documentation. Troubleshooting process should be guided by structured methods such as 7-step troubleshooting process, which is, of course, define the problem, gather information, analyze the information, eliminate possible causes, propose a hypothesis, test that hypothesis, and then solve the problem. Troubleshooting tools such as network management station tools, knowledge bases, baseline tools, protocol analyzers, digital micrometers, cable testers, cable analyzers, portable network analyzers, Cisco Prime NAM and Syslog servers can all give you troubleshooting information to help give you a clue what the problem is. Physical layer problems cause failures in suboptimal conditions. Data link layer problems are typically caused by encapsulation errors, address mapping errors, framing errors, and STP failures or loops. Network layer problems include IPv4 and v6 routing protocols such as EIGRP and OSPF. Transport layer problems can be misconfigured NAT or ACLs. Application layer problems can result in unreachable or unusable resources. A bottom-up troubleshooting method can be used to solve connectivity problems. Start verifying the physical layer, check for duplex mismatches, verify addressing and default gateway, verify the correct path is taken, and verify the transport layer. There's the logo. So I'll see you again for chapter 13. Goodbye.